Hello everyone, Mr. Fawcett here, and we are back with another Algebra 1 lesson. Right, this is actually part 2 to our exponential functions lesson. In the first part of the lesson, we got an introduction to the difference between what a linear function is versus an exponential function, and we practiced graphing exponential functions. We also talked about the different characteristics of graphs of exponential functions. Today, we're actually going to do the opposite. So if we scroll down here, we are going to try to come up with an equation of an exponential function based on a table of values, and then we'll eventually look at coming up with an exponential function based on a graph itself. And then finally, we will end with some word problems and trying to decide whether the word problem represents an exponential function scenario or maybe just a linear function scenario. So let's start up here with our tables. And just a quick review from our previous lesson. If I'm looking at the standard form of an exponential function, well, that's going to be y is equal to a times b to the x. So our x is in the exponent. That's why it's called an exponential function. Now the a, right, that represents our initial value or our y value, or sorry, y-intercept. So initial value or y-intercept, and our b, that represents the constant ratio. So if we're trying to build out our equation here, well, can we identify the y-intercept from the table? Well, for our y-intercept, what is our x value always going to be? Right? If I have a graph here, a random graph, doesn't matter if it's exponential graph or whether it's I'll draw an exponential graph because that's what we're looking at. But it's same thing for linear as well, right? The x value for every y-intercept is going to be 0. I may not know what that exact y value is, right? But I know that the x value for that point is 0. So if I can find a 0 for my x in the table, that is going to give me my y-intercept. In this case, they do give me a 0 for my x, and I know that my y value when x equals 0 is 0.4. So I can start by saying y is equal to 0.4 times, now I need to figure out my constant ratio. Well, the constant ratio is what am I multiplying by to go from one y value to the other, right? As long as my x is increasing by 1 each time. Well, you could try to do this in your head, or I'll show you a way to do it on paper. But maybe if you did it in your head, you see that, well, I'm multiplying by 5 each time. Right? 0.4 times 5 is 2, 2 times 5 is 10, 10 times 5 is 50. So our function is growing at a rate of a multiple of 5 every time. Right? If I increase the x by 1, my y is going to increase by a factor of 5. So if I go back to my equation, this is going to be 0.4 times 5 to the power of x. That is the equation of this exponential function. Now you may say, well, what if I couldn't tell that it was 5? Right? Because some of these may be 5.8 or 1.4 or 2/3, etc. Well, if it's not clear to you what you're multiplying by every time, then there's an easy way to figure out what this constant ratio is. And that is to actually write out the ratio, right? A ratio is just a fraction. So what you do is you take one x value. So let's say let me erase some of this. You take one x value, I'm going to take 2, and divide it, sorry, did I say x value? I meant y value. Take one y value and divide it by the previous y value. So 2 divided by 0.4, that gives us 5. Now this should work for any of them, right? Let's take 10. So 10 divided by 2, that also gives us 5, right? And you could do 50 divided by 10, and that would also give you 5. It doesn't matter which one you choose. If it's an exponential function, that ratio is the same, right? That's why it's called a constant ratio. I'm not multiplying by 5 one time and 6 the next time. It's going to be multiplying by 5 every single time. Notice that if you had done it the opposite way, maybe you messed up which numbers you put in the numerator and denominator. So let's say you did, let's just say you did 2 divided by 10. You get 1/5. Well, you should know intuitively that this doesn't make sense, right? Because if I'm going from one y value to the next, these y values are increasing. So, but if I multiply by 1/5, that would make the number smaller. It would get it closer to 0. But these y values are going away from 0. They're getting larger. So in this case, 1/5 would not make sense for the constant ratio. And you'd realize that, well, I actually need to switch these numbers, and that will give me the correct constant ratio, 5/1 or just 5. So see if you can apply this process to number 2, both find the y-intercept as well as find the constant ratio. So pause the video and then come back and see if you get it right. Okay, so for number 2, y-intercept is 11. So I get y is equal to 11 times, well, this one might be easy to tell what the constant ratio is. Right, we are multiplying by 3 every time. So we get y equals 11 times 3 to the power of x. That is our equation. Again, if you wanted to write out the ratios, you could. Right, you do 33 over 11. That gives you 3. You could do 99 over 33. That gives you 3. Or you could do 297 divided by 99. That also gives you 3. So again, that's a way to figure out what the common ratio is if it's not clear to you. Now remember, these ratios don't always have to be numbers greater than 1, right? It has to be a number greater than 0, but we could also have some fractions. So let's take a look at some of those examples for 3 and 4. Pause the video, see if you can do 3 and 4, and then we'll real quickly talk through them together. Or at least let's just talk through number 3. If you can do number 3, you can certainly do number 4. So we'll just go over one of them. All right, so y-intercept, 60. So I get y equals 60 times, well, what am I multiplying by to go from one y value to the next? Well, this may not be clear, right? What do you have to multiply 60 by to get 15? Well, if it's not clear, set up your ratio. So in this case, 15 over 60. If you simplify that, you get 1/4. Check to make sure the other ratios are the same. If I do 3.75 over 15, this also gives me 1/4. Notice that these also give you 0.25. All right, so if you wanted to use 0.25, you could. The only time I would allow you to use a decimal when you're writing out your equation like this is if the decimal terminates. So because 0.25 terminates, it doesn't repeat, it doesn't go on forever, you could use the decimal. I'm probably going to write it with the fraction, but again, 1/4 and 0.25, those two are equal to each other, so you could use either one. And of course, you could do this last ratio to check. 0.9375 all over 0.375. That also gives you 1/4 or 0.25. So our equation becomes 60 times 1/4 to the power of x. Now it's important that you put 1/4 in parentheses because that x exponent is being applied to the entire fraction. It's not just being applied to the 1. So if you just left it like this, right, that means that the exponent's only being applied to the 1, the numerator. So we need the parentheses right here when it's a fraction. Okay, let's do an example right below because these are actually different and much tougher. Let's do number 1. Take a second, pause the video, and see what's different about this one than the previous ones that we've done. So you may want to work it out, and maybe you'll be able to get it, maybe you won't, but there is a key difference. Okay, so hopefully you see that our y-intercept is not given here, so we have to come up with another way to find that. And we're going to approach this differently than the ones we did before. So because we can't figure out the y-intercept first, we're actually going to figure out the constant ratio first. So we can think, again, what are we multiplying by to go from one y value to the next? And it's okay if we write this as g of x, right? Y or g of x, they mean the same thing. They're both our outputs to the function. This one's pretty clear. I think it's easy to see we're multiplying by 2 each time, so our constant ratio is 2. You could write out the ratios, right? 12 over 6 is equal to 2, 24 over 12 is equal to 2, and 48 over 24 is equal to 2, if you didn't see that right away. So I know that my equation is going to be y equals a, I don't know what my y-intercept is, so I'm going to leave it as a, times 2 to the power of x. Now how do I figure out that a? Well, let me take one of these points, 1 comma 6, right? So my point, 1 comma 6, let's make that substitution. So y is equal to 6, 6 is equal to a times 2, x is equal to 1. Well, 2 to the power of 1 is just 2, so I get a times 2. And then I can just divide both sides by 2. So I get a is equal to 3. So my y-intercept is 3 here. Then I can go back and write the full equation. Going to get y is equal to 3 times 2 to the power of x. And there's my equation right here. So if the table does not give you your y-intercept, you're going to set up an equation after finding your constant ratio and use one of the points from your table to substitute in and solve for the a, or the y-intercept. You can try number 2 on your own. I'll put the answer up here. So pause the video, do it, and I'll put the answer up and you can check. All right, so I'm not going to go through it for time's sake, but this answer would be y is equal to, our y-intercept ends up being 5. Our constant ratio is 3. So y equals 5 times 3 to the power of x. Okay, let us try one with a graph. You know what, let's do, this doesn't really matter too much. Let's do number 1. So this is basically the same, right? The only difference is your points are on a graph rather than in a table. So it works the same way. In fact, I even give you the points here. You don't even have to label them yourself because these ones are not clear exactly where they're at, so that's why I write them down for you. So go through the same process, try to figure out the y-intercept, the constant ratio, and come back and see if you did it correctly. Okay, so y-intercept here is 2, right? That's given from this point. When x is equal to 0, y is equal to 2. So I get y is equal to 2 times my constant ratio. Now, these are not written in table form, but essentially we're trying to figure out what am I multiplying by to go from one y value to the next. So 2 to 8, 8 to 32. Well, I'm multiplying by 4. 4 is my constant ratio here. So 2 times 4 to the power of x. If you didn't notice that it was 4 and you wanted to write out the ratio to figure it out, well, you could just set up your own table, right? X and y table. We get 0, 2, 1, 8, 2, 32. Then you could set up your ratios 32 over 8. That's 33 though. 32 over 8 is equal to 4, and 8 over 2 is also equal to 4. Okay, I think that's enough practice, at least for the video, with writing out exponential functions, or the equations of an exponential function. Let's now get into some word problems. So for these word problems, we're first going to decide whether the situation represents a linear function or whether it represents an exponential function. Once we decide whether it's linear or exponential, then we can try to go ahead and write an equation for it. So we'll go do both of these. Again, first thing, try to think about whether it's linear or exponential. Then we'll get into writing the actual equation of this function. And I know it says we're writing a function. Again, we're going to write it in equation form. So we're not going to use f of x or g of x. We're just going to use x's and y's. Just because it's x's and y's doesn't mean it's not a function. It's just not necessarily in function notation, right? But it's still considered a function. So read through both of them and see if you can determine which one is exponential and which one is linear. All right, so the first one says, Jenna oversees stacking bags of oranges on the display shelf during her shift at Walmart. Each bag contains 8 oranges, and Jenna places a new bag on the shelf each minute. The shelf had 112 oranges on the shelf to begin with. I guess we could just say on it to begin with. So it says, let x represent the number of minutes since Jenna started working, and let y represent the total number of oranges on the shelf. So basically, to decide whether it's linear or exponential, we need to think, is the amount or the quantity of oranges changing by a constant amount every minute, or is it changing by a constant ratio or rate every minute? Right? So is the same number of oranges being added every minute, or are we multiplying the total amount of oranges every minute? Well, if she places one new bag on the shelf each minute, the number of oranges is increasing by 8. So it's increasing by a constant rate, right? 8 oranges per minute. So that makes this a linear function. So if it's linear, we're going to write it in the form y equals mx plus b, where m is our y-intercept. Sorry, m is not our y-intercept. M is our slope, and b is our y-intercept. Well, can we figure out either of those? Do we know what our y-intercept is? Do we know what our slope is? Well, it says the shelf had 112 oranges on it to begin with. So that's essentially our initial value. That is our y-intercept. When x is equal to 0, right, and x is the minutes, so when 0 minutes have passed, well, there's 112 oranges on the shelf, because that's the amount that was there to start. So I don't know quite what my slope is yet, but I know my y-intercept is 112. Well, the slope is just how much is the total, or how by what number does the y value increase or decrease as we change the x value? Well, for every new minute, there are 8 new oranges added to the shelf, because every bag contains 8 oranges. So we are increasing our y value by 8 each minute. So y equals 8x plus 112. That would be the function or the equation that represents this scenario. If you didn't want to write this using slope-intercept form, you could write it using point-slope form. Now, they give you 1 point to begin with when they say it had 112 oranges on it to begin with. So that point would be 0, 112. If you wanted to figure out a new point, well, you could think about, okay, after 1 minute, so when x is equal to 1, well, there were 8 new oranges on the shelf, so there would be a total of 120 on the shelf. So you could come up with that new point there and use those 2 points to find your slope and to write your equation in point-slope form, right? Y minus y1 is equal to m times the quantity x minus x1. It takes a bit more time, but maybe you didn't understand how to write it in slope-intercept form first. So just another way of figuring out what the equation is, you could always think about starting from point-slope form as well. Okay, let's check out the next example. This one says Brittany created antibodies to fight a certain virus. She initially created 100 antibodies, but the antibody population can triple itself every minute. Let x represent the number of minutes and let y represent the total number of antibodies. So we have to think, as the time increases, are we changing the number of antibodies by a certain amount, like the same amount every minute? Do we increase the number of antibodies by the same amount? Or are we changing it by a certain factor? Are we multiplying the number of antibodies by a certain number every time? Well, up here, it says the antibody population can triple itself. And that means we're going to multiply it by 3 every minute. So we start off with y equals a times b to the x. Our initial value is 100, right, because there were 100 antibodies to start. And if we're tripling it, well, that means our constant ratio is 3. So y equals 100 times 3 to the x. Again, triple is going to mean multiply by 3. If you're trying to think about, well, why isn't this linear? Maybe you were thinking, well, this could have been y equals 3x plus 100. Why doesn't that work? Well, let's think. After 1 minute, right, if the number of antibodies triples every minute, after 1 minute, there should be 300 antibodies, right? Well, if I substitute in 1 for x here, at x equals 1, I get y is equal to 3 times 1 plus 100. Then 3 plus 100 is just 103. So this linear equation would just mean that the number of antibodies increases by 3 each minute. Whereas the exponential equation over here means that it increases by a factor of 3. Okay, so there's a big difference between adding 3 every time versus multiplying by 3 every time. And triple means that we are multiplying by 3. All right, that is going to do it for this lesson. As always, enjoy the rest of your day, and we will look forward to seeing you next time with a new unit.